turn on subtitles for better experience. Tachyons are one of the most interesting elements arising from Einstein's theory of special relativity. The 1905 theory is based on two postulates. Nothing with mass moves faster than the speed of light, c, and physical laws remain the same in all non-inertial reference frames. A significant consequence of special relativity is the fact that space and time are united into a single entity called space-time. That means a particle's journey through speed is linked to its journey through time. The term tachyon first entered scientific literature in 1967 in a paper entitled Possibility of Faster Than Light Particles by Columbia University physicist Gerald Feinberg. Feinberg posited that tachyonic particles would arise from a quantum field with imaginary mass, explaining why the first postulate of special relativity doesn't restrain their velocities. This would lead to two types of particles existing in the universe: bradyons that travel slower than light and compose all the matter we see around us, and tachyons traveling faster than light, according to the University of Pittsburgh. One of the key differences between these particles types is as energy is added to bradyons, they speed up, but with tachyons, as energy is taken away, their speed increases. One of the most important and meaningful results from Einstein's theory of special relativity is the establishing universal speed limit of c, the speed of light, in a vacuum. Einstein suggested that as an object approaches c, its mass becomes near infinite, as does the energy required to accelerate it. This should mean that nothing can travel faster than light, but imagine an antimass particle like a tachyon. Its lowest energy state would see it speeding at c, but why would this lead to backward time travel? That all hinges on the concept that puts the relative into special relativity. A common tool used to explain special relativity is the space-time diagram. Space-time is filled with events ranging from the cosmically powerful and violent, like the supernova explosion of a distant star, or the mundane, such as the cracking of an egg on a kitchen floor, and these are mapped onto the space-time diagram. This diagram shows as a particle whizzes through space-time. It traces out a word line that maps its progress. Also, filling space-time are observers, each of whom has their own reference frame. These observers may see the events that fill space-time occurring in different orders. Observer 1 may see event A, the supernova, occur before event B, the egg cracker. Observer 2, however, may see event B happening before event A. Each event has a light cone associated with it. If event B falls within the light cone of event A, then the two could be casually linked. The supernova could have knocked the egg off the kitchen counter, or maybe the falling breakfast item caused the complete gravitational collapse of a dying star somehow. That's because in the light cone, a signal traveling slower than light can link the events. The edges of the light cone represent the speed of light. Linking an event outside the light cone with one inside it requires a signal that travels faster than light. If event A is in the light cone and event B is outside it, then the supernova and egg related tragedy can be usually related. But a tachyon traveling at a speed greater than the speed of light could violate causality by linking these events. To see why this is a problem, consider it like this. Image event A is the sending of a signal and event B is the receiving of that signal. If the signal is traveling at the speed of light or slower, all observers in different reference frame agree that A preceded B. But if that signal is carried by a tachyon and thus moves faster than light, there will be reference frames that say the signal was received before it was sent. Thus, to an observer in this frame, the tachyon traveled backward in time. One of the fundamental postulates of special relativity is that the law of physics should be the same in all non-accelerating reference frames. That means if tachyons can violate causality and move backwards in time in one reference frame, it can do it in all them. Paradoxes. To see how this leads to a problem called paradoxes, consider two observers, Stella, aboard a spacecraft orbiting Earth, and Terra, based on the surface of the planet. The two are communicating by sending messages with tachyons. This means that if Stella sends a signal to Terra which moves faster than light in Stella's frame but backward in time in Terra's frame, Terra then sends a reply as ordered which moves faster than light in a frame but backward in time in Stella's frame. Stella could receive the signal before sending the original signal. What if this response signal from Terra says to not send any signals? Then Stella does not send the original signal and Terra then has nothing to respond to and never sends the tachyon signal that says don't send any signals. So not only do tachyons violate causality in every frame, they open the door to serve logical paradoxes. Their suggestions. These paradoxes could be avoided. Of course, the most simple solution is that tachyons don't exist. A less draconian suggestion is that observers in different reference frames can't tell the difference between the emission and absorption of tachyons. That means a tachyon traveling back in time could always be interpreted as a tachyon moving forward in time, because receiving a tachyon from the future always creates the same tachyon and sends it forward in time. Another suggestion is that tachyons aren't like any other particle we know of, in that they don't interact and never be detected, meaning that the tachyon communicating system used by Stella and Terra in the above example can't exist. Along similar lines, other researchers say that tachyons can't be controlled. The receipt and emission of tachyons just happen at random. Thus, there is no way to send a tachyon with a causality violating message. Aside from this fact that like other particles, they are likely incomprehensible tiny. Because tachyons always travel faster than light, it isn't possible to detect one on its approach. That's because it moves faster than any associated photons. After it passes, an observer would see the image of the tachyon split into two distinct images. These would show it simultaneously arriving in one direction and disappearing in the opposite direction. If detecting tachyons at least of the approach with light is out of the picture, is there any other way we could detect these faster than light particles? Possibly. Tachyons are proposed to have an anti-mass, but this still constitutes mass energy. That means these particles should still have some gravitational effect. It's possible highly sensitive detectors could stop this effect. An alternative detection method could arise from the faster than light nature. While the speed of light in a vacuum c is a universal speed limit, particles have been made to travel faster than light in other mediums. When electrically charged particles are accelerated up to and beyond the speed of light in certain mediums like water, they release a form of radiation called Cherenkov radiation, according to the International Atomic Energy Agency. That means if tachyons are electrically charged, one way of detecting them would be measuring Cherenkov radiation in the near vacuum of space. What tachyons really demonstrate is the importance of imagination in an ongoing quest to understand the universe. They may not exist, and if they do, we may have no hope of ever measuring one. But what our technology can't capture, our minds can. We can consider the possibility of a particle that journeys back through time and what that says about the nature of time and the universe and the events that fill them. In an interview with George Sylvester Viereck published in the Saturday Evening Post in 1929, Albert Einstein is believed to have said, "Imagination is more important than knowledge. Knowledge is limited, imagination encircles the world." Thank you for watching, and don't forget to tell your thoughts in the comments below.